All right, good morning, Astronomy 1020. Welcome to our fourth lecture. We didn't do an office hours today because we're trying to get our lectures a little bit ahead of the homework since we're doing our homeworks in the morning. We're going to enter chapter 4, which is Newtonian mechanics. We're going to learn about forces and gravity. Obviously, that's going to be important if we want to study stars. This also represents a small boost in mathematical complexity. So have those Casio FX260 solar calculators on hand because you're going to get a lot of training on them today if everything goes according to plan. Okay, so in our last class, we learned that a famous German astronomer mathematician named Johannes Kepler had derived some laws. Let's see if I have them in this. Yeah. Johannes Kepler, German mathematician, had derived several laws that correctly described the orbits of planets in a Copernican solar system. Function F5, 55. So here's our, our painting of the great Kepler. And you guys learned that he had 3 laws of planetary motion, which described how planets orbit around the sun. These are extremely useful. That's why they have been codified as laws in physics and astronomy. They are technically not perfectly true, but they are true in so many instances, and 99% of the time, that they end up being a very useful thing to study and a good starting point. Kepler actually was a little bit of a mystic and a weirdo. He wrote this famous book called Harmonious Mundi, on the harmony of the spheres. And one of the things that he planned on doing with his laws of orbital mechanics is he wanted to describe the periods of the planets so he could discover the music of the universe. And so after he derives his equation p squared, shoot, this isn't right. Kepler Harmonices Mundi, sorry about that. After he derives his p squared equals a cubed, his book suddenly breaks into song, and he uses the periods of the planets to compose their natural song. So there was a sort of frequency, a resonant frequency for Mercury, and one for Venus, and one for Jupiter. Pretty wild and weird stuff if you actually look into it. However, his laws stand today as extremely useful in describing how planets and stars orbit one another. Kepler also meditated on the fact that planets were orbiting. Well, let's see. You guys remember your 3 laws of planetary motion, right? What's the first law? The summary version. Ian's eating, so he gets a pass. Sage, Ryan?
A planet orbits the sun on an ellipse with the sun located at a focus point.
Okay, let's see. Right. Okay, and what about the second law?
A planet sweeps out equal units of area and equal units of time.
That's right. And Kepler wondered about this. He believed that there was some kind of living vitality that connected the planets to the sun. And he wrote that you can see them speeding up as they approach their perihelion. It's as if they are given some sort of dynamic energy from the sun, or I don't know what sort of mystical terms he used. But he was missing a key idea. And the key idea was that there was a force of gravity between the planet and the sun. This concept of force and gravity were properly developed by another great physicist named Sir Isaac Newton, who came about 100 years after Kepler. And a lot of Newton's work was based on the work on orbital mechanics that Kepler had done. Today we study all things Isaac Newton, and that's the subject of chapter 4. In particular, what our goals are today, if I can not screw this up. So here we are, Sir Isaac Newton. People consider him right up there with Einstein as probably one of the greatest physicists of all times, because he didn't just discover maybe like one thing or 2 things, but like 10 or 15 different things that were all revolutionary game changers in the world of physics and in mathematics as well. Probably the single biggest idea that we associate with Sir Isaac Newton, and we'll talk about it extensively today, is the concept of a force. And there's the term force, but Newton codified it and put it on strict mathematical terms so we could understand exactly what we mean by such a thing. In the general usage, force is supposed to be either a push or a pull. So that's the kind of conceptual idea behind it. But he related forces to motion and acceleration. In particular, today we will attempt to study two of the laws that he derived in his legendary book, Principia Mathematica. I've got a copy of the Principia right here on my shelf. It's now considered a classic of Western philosophy. It's transcended physics in its profundity. And what we're going to work on today is studying his three laws of motion. The three laws of motion give us good judgment about how bodies move once they are subjected to forces. In particular, in the three laws of motion, we study how bodies move when they're subject to an arbitrary force. And that force could be just about anything, from gravity to friction to punching your little brother in the nose, okay? And if you specify the force, Newton's laws of motion will tell you how the objects will move or accelerate based on that. As a sort of separate concept, although they are often used together, he also derived something called the law of gravitation. This is where he sort of spelled out mathematically how gravity works to attract bodies by dint of mass. And the law of gravitation is different from the laws of motion because they involve what we call in physics a fundamental force. Fundamental forces are cool because they are essentially a mystery of nature. Fundamental forces like gravity are built into the machinery or the board game that is the universe. And although it's awkward to ask questions like, why does gravity exist? We attempt to understand it and quantify it and predict what will happen when bodies interact through gravity. Do you guys remember how many fundamental forces there are? My 1010 students?
Is there 4?
Yeah, historically there were 4, although they've been collapsing in the last 20 or 30 years, right? So the classic 4 fundamental forces, and we'll do them, geez, how do I want to do this here? We could do this in random order, okay? Let's do them in random order. Gravity, electromagnetism, the strong nuclear force. I learned about these when I was a kid, so I would expect you guys to have heard of this before.
I think the first time I heard about these was in a history class, weirdly enough, in high school.
In a what?
History class in high school.
In a history class.
Yeah, it was
That
big
is
history,
very...
so it was like the whole universe. It was cool.
Oh, wow. That sounds like it could have been an interesting teacher who's doing their class. The strong nuclear force and the weak nuclear force. And if you were to rank them in order of strength, which probably doesn't seem that important to you right now, 1, 2, 3, 4. Gravity is actually the weakest, but gravity is sort of one of the most obvious because it's so easy to observe in our everyday lives. As I mentioned before, the modern standard model of physics has made some success in collapsing electromagnetism, the weak and strong nuclear forces, into what is known as the standard model of physics. And some people believe that all of these fundamental forces are aspects of the one force, the theory of everything, a single mathematical equation that would describe the evolution of all particles from the Big Bang to the heat death of the universe. And that's some cool Yoda-like crap that is fun to think about. And a lot of research in physics is done into trying to explore these relationships. Gravity tends to affect objects on macroscopic scales. Gravity is so weak, in fact, that you don't even begin to notice it until you build up a planet's worth of matter under your feet. And then you think, things fall down and go boom. But when you try to analyze how gravity works with the world of microscopic things like atoms and protons and electrons, the force of gravity is so weak as it's very difficult to design experiments which can compare what happens when these two things interact. That so-called theory of quantum gravity is this elusive beast that many scientists search for today. You'll get your first taste by studying Newton's law of gravitation. That was one of the first really good developments of our understanding of gravity. If we're going to do this stuff, we're going to have some background talk first. So let's do some background talk. Do you guys mind if I erase this stuff? Okay. There's going to be several equations. Up to now, we've done maybe like one formula per chapter or so, but there's going to be like 5 this chapter, and they're going to be intense. All of the formulas we use in this chapter are going to conform to a particular set of units. So let's have a discussion about the MKS system of units. You guys know from my lectures that units are a big deal that we have to pay attention to. The quantities that we often concern ourselves with in physics are quantities like length, mass, time, and there are a few other fundamental quantities that come up in physics. Things like elementary charge and magnetic field strength, but we'll leave those aside for now. We'll just focus on 3 of the basics. We can measure length, mass, and time in a variety of different units. In the imperial system, which we use in the US, I think the default measurement for length is feet, which is a little bit goofy. Because we're going to be using the metric system, our fundamental unit of length is going to be the meter. The meter is the gold standard for measuring lengths in physics. Abbreviation 1M. The standard unit of mass is the kilogram, 1 kg. And of course, the fundamental unit of time is the second in both metric and imperial units. Taken together, the set of units, meters, kilograms, and seconds, are sometimes referred to as the MKS system of units. And all formulas must be converted to these units before we can plug numbers into them. And I want to state that right up front. Probably one of the most useful conversions you're going to need today that we've already discussed is that 1 kilometer is equal to 1,000 meters. So that comes up all the time in this class. But we may also need some other units of measurement. 1 meter is 100 centimeters. 1 centimeter is 10 millimeters. These are ones that come up in our class frequently. Every now and then we have to mess around with grams. 1 kilogram is 1,000 grams. Not too often. Those are some basic metric conversions that you might even already have known, either from life or just from some basic science class. Okay, now that I've got that out of the way, as we talk about some various concepts today, let's not only pay attention to the definitions, but let's pay attention to the units, and let's pay attention to how they resolve into the MKS system. That's going to turn out to be a smart thing to do. Newton's laws of motion deal with quantities like acceleration, and we also have to talk about things like velocity. So I thought we would have a quick review of those things in case you forgot how they work. I'll try to keep this part brief because it's real basic background stuff. But sometimes there are students who take my class who haven't heard this spiel before, And so it's important to go over it. Distance and time are related by velocity. Velocity is related to another word, speed. And although the two things can be used interchangeably, they have technically different definitions. Do any of my students from Astronomy 1010 remember the distinction between velocity and speed?
What I have written down and my basic understanding of it is speed is just how fast you're going, and it's 1D motion. And then velocity is speed and direction, so it's 2D or 3D motion.
Or even 4D if you do special relativity. But more on that later. That's exactly right, Ian. So you did it great. So we have speed. Speed is a quantity that we measure in units of meters per second. It tells you how fast. I like everything that he said. It's a description of 1D motion. It tells you how fast you're traveling, but not which direction. It has no direction associated with it. Velocity is considered a speed plus a direction. So for instance, if you have a velocity of 5 meters per second, and then you specify 30 degrees east of north, this constitutes a velocity because of the directional information. And of course, velocities are confusing compared to speed because you can change velocities by changing how fast you go, but you can also change your velocity by changing your direction. And one place where this comes up very frequently in astronomy is to consider perfectly circular motion, like a geosynchronous satellite or something, right? In the situation of a satellite, which we'll consider in lab today, a satellite makes a perfectly circular orbit around the Earth. And because it's traveling in a circle, it's probably traveling at a very uniform speed. I don't know the exact speed of the ISS, but it's quite fast. It can go around the Earth in a couple hours. The speed remains constant, but the velocity is changing because at one moment, the direction of motion of the satellite is sort of over to the right. But a few moments later, as the satellite, excuse me, moves in orbit, at this point of the orbit, the direction of the velocity might be sort of over here. So the rate at which the satellite travels through space remains constant, its speed remains constant, but the direction is constantly changing, and therefore it's considered to have a non-constant velocity. Its velocity is changing. We're interested in these things because changes in velocity are related to another quantity that comes up in Newton's laws called acceleration. Let's include Ian's suggestion that velocity is a 2D or a 3D or a multi-dimensional description of motion. Okay, I'm going to erase that. I have slides for this stuff, but this is background stuff. I kind of want to crunch through it faster so we can get to some of the crunchier math bits. So I'm trying this out. Let me know if it's working for you guys. Erasing. Okay, let's have a discussion of acceleration. Usually we use a lowercase a for acceleration. And the definition of acceleration is a change in velocity divided by a change in time. On the other hand, since everything sort of takes time to do, you can almost ignore the change in time part and you can just say a change in velocity. That's loosey-goosey, all right? However, if you want to state it mathematically, you'd have to consider something that changes its velocity. And here I will rely on a slide. Boink, boink. If we want to talk about it mathematically, we have to include the time because the definition is change in velocity is represented by delta V over delta T, where delta explains that we're going to be subtracting two velocities, and here we're going to be subtracting two times. So a classic example of acceleration is if you just kind of drop a ball off the top of a building. If you hold it in your hands very still and very carefully, Sage, I don't know if you're afraid of heights or something, but anyways, you just do, all right. So you hold it in your hands and the velocity is 0 at the start of the experiment, and you release your hand and the magic of gravity begins to work and begins to pull the ball down to the ground. As the ball drops towards the ground, its velocity is going to change because it went from not moving to suddenly magically moving, and the rate at which it travels goes faster and faster if you can keep measuring it. So we can talk about the change in velocity with respect to time by analyzing its velocity at two different points, say at time equals 1 second and at time equals 2 seconds. And let's just do that for a moment because it's kind of useful. So mathematically speaking, I think I'm going to get a fresh marker here. Uh-oh, very last one. So an acceleration could be described as a change in velocity divided by a change in time. For those of you who don't speak math, that little triangle is the symbol delta, and it's shorthand for velocity 2 minus velocity 1 over t2 minus t1. How much did our velocity change divided by how long did it take to change that velocity? If you perform the experiment where you hold a ping pong ball and you release it from your fingers and it begins to move, you can attempt to measure this as the great Italian physicist Galileo Galilei did by means of what Newton would call an artificer, okay? Newton refers to experimental science machines as artificers, things that are going to measure the properties of nature by some clever stratagem. Of course, in Galileo's version, his artificer was the inclined plane. And this is the stuff, of course, of legend. Galileo wanted to measure how the velocities of objects changed as they fell to Earth. He didn't have modern tools like laser gates and high-speed photography. So what he did is he built an inclined plane that would sort of slow the rate at which objects fell towards the Earth. Actually, rate is an improper term here. Slowed the acceleration with which objects fell to Earth. And he measured the change in velocities by means of this artificer. He put these little bells on the top of the ramp so that as the particle or the steel ball rolled down the ramp, it would tinkle the bells, and he could time, using his ear, the increase in speed by the cadence of the ringing of the bells, which is kind of brilliant if you think about it. So Galileo was, in a sense, the first person to discover or measure an acceleration. And this is exactly what Isaac Newton meant by an artificer, some sort of clever tool to study the properties of physics. Okay, when you perform the experiment, you find that if you drop a ball from rest, that after 1 second, it has a velocity of 10 meters per second. And after 2 seconds, it has a velocity of 20 meters per second. And what we'd like to do is take 2 points in this experiment and plug them into our acceleration just for fun. Okay, so we'll take T1 and T2, and our acceleration would then be 20 meters per second minus 10 meters per second divided by 2 seconds minus 1 second. You guys know that 20 minus 10 is 10 meters per second. 2 minus 1 is 1 second. 10 divided by 1 gives us 10. And now we want to analyze the units of acceleration. Sage, my mathematical friend, do you know the units of acceleration?
I like want to say meters, but it feels like that's not correct. I feel like it's meters over second squared, maybe.
Yeah, so how do we, there's a little sign on one of the professor's doors on the hall that I walk down every day, or used to walk down every day. And it said, 3 out of 2 people are bad at fractions. And that applies to CCRI as well. Here, Sage, we have the problem of a fraction divided by it within a bigger fraction. How do we handle such a thing?
Yeah, so it would be multiplied up top and it would cancel out the S's, but I feel like acceleration is a measure of time and meters, so I was a little bit confused about that.
Yeah, something's not right, and you can feel it. All right, Sage, it's time for us to play a little game that will benefit not only you, but many other people in this class. It's how we deal with fractions within fractions. I want you to consider this a Zelda mini game that we're about to go into, and it's a most necessary mini game. Okay, let's use pretty colors so we don't terrify the heathens, okay? And let's imagine that we had 2 fractions. I'm going to use letters here. So we have A divided by B on top, on the top of the fraction. And on the bottom, we're going to do C divided by D. And these are all different numbers. And we've got ourselves 2 fractions within a bigger fraction. The goal is to simplify or reduce the fraction into a single fraction with some letters on top and some letters on the bottom, okay? Now, because I occasionally am going to need to talk about things like this and it's awkward, I have little nicknames for these things. A, I call the top of the top fraction. B, I refer to as the bottom of the top fraction. Okay, the top of the top, the bottom of the top. Here we have the top of the bottom fraction, and then D will be the bottom of the bottom fraction. I'm tempted to make an off-color joke, but I'm going to refrain from doing so. Okay, now let's start by, I once heard in a math, I actually went to a few math lectures once just because I wanted to figure out what all these math professors were up to. I wanted to see some people who are truly divorced from reality. But I remember one thing that they said once that was very interesting. And they said, anytime you're confronted with a difficult problem that you can't solve, solve a simpler problem that's similar to that one and see if it gives you any insight. So one way we can intuitively analyze this if we ever get confused is by plugging in some fake numbers and trying to keep them as simple as possible. For instance, we could experiment by plugging the number 2 in for one of these letters and setting all of the other letters equal to 1. And that usually tells you what to do. For instance, if you did 2 divided by 1 over 1 divided by 1, I suspect that most of you knew that reduced to 2. And what that suggests to me is that the top of the top should remain on the top. Okay, Sage. Since you're our resident math expert here, how about B, the bottom of the top?
Sorry, that should probably stay underneath.
Yeah, and we can test it, right?
Yeah.
We can test it by substituting in a 2 here. And what does this reduce to?
That would go into 1/2.
Yeah, because 1/2 divided by 1 is what. And so that suggests that the bottom of the top fraction should end up on the bottom. Okay, how about C? The top of the bottom.
That is going to flip and end up on the bottom.
Well, it's not flipping, it's staying where it is. That's how I look at it, right?
Okay.
C is the top of the bottom. Well, okay, I guess my knowledge of how to solve this is so ingrained to how to do it right that it's weird. But if you do 1 divided by 1 over 2 divided by 1, the top becomes 1 and the bottom becomes 2. And so the top of the bottom stays at the bottom.
Yeah.
Now, the one that I've noticed really screws the hell out of people, that really messes them up, is the bottom of the bottom fraction. This one really causes people some trouble. And the way to analyze that is by the same procedure. If you do 1 divided by 1 over 1/2, you have to sit there and meditate on what does 1 divided by halves mean? And one way to think about that is 1 is an entire pizza. Usually it's fun to think about pizzas, okay? So if you had a whole pizza and you divide it into half pizzas, you end up with 2 half pizzas, which suggests that the bottom of the bottom fraction, D, should flip back up to the top. Lovely. Okay, now a moment ago, you told me that the seconds were going to cancel out.
Yeah, they're not going to. They're going to multiply together. I was inversing the top, not the bottom, and multiplying them together.
But there's no need to inverse the top. You don't invert.
I know. You invert the bottom, the denominator.
Or it's rather that the bottom of the top should drop down, something like that. Okay, however you want to say it.
Makes sense to me.
We
Sorry.
understand now that it's meters divided by seconds times seconds, right? By the way, Sage, I didn't just do that for this example. There's going to be a lot of unit canceling that's going to get more sophisticated. And starting there is actually a good thing for all my students to do, okay? All right, so of course, if it's 10 meters per second, we can represent that as 10 meters per second squared. Okay. This experiment that Galileo did, where he dropped spheres on inclined planes to measure the natural acceleration of Earth, is a really big deal in all of physics. This acceleration, which is unique to the planet Earth, is so important that we don't even just describe it with the letter A, we give it its own variable, and we call it little g, lowercase g. And this is what is known as the local acceleration of Earth's gravity. Now, you do not want to call this gravity. Gravity is an abstract concept. This is the local acceleration of Earth's gravity. And one of the key discoveries that Galileo made, and this was important because before Galileo, people's conception of physics was based on Aristotle's original textbook called Physics. Aristotle had claimed that if you have 2 stones, a massive stone and a light stone, and you dropped both of them at the same time, that more massive stones would fall to Earth faster by dint of something he called gravitas, okay? So that word is quite old. Galileo discovered that Aristotle was lying, or rather, he had been, what's the word? Incompetent, because he did not go about testing his assertions, as a good scientist should. Galileo discovered that all objects accelerate to Earth. Okay, I'm running out of room here. At the same acceleration. I keep wanting to say the word rate, but you can't do that because rate means speed, okay? All objects accelerate to Earth. Let's put it this way. At little g, at 10 meters per second, or 10 meters per second squared. As I mentioned previously, this experiment has been reproduced countless numbers of times, including, let's take a trip down US space history lane here, by Neil Armstrong. When he stood on the surface of the moon, he dropped a feather and a hammer on the airless surface of the moon.
Jim, we copied both solar wind and penetrometer drum
Pretty
in the
cool,
ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got...
Beautiful picture, Dave.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Hold on.
Penetrometer drum.
If Neil Armstrong can take 1 minute and 30 seconds out of the first landing on the moon to talk about Galileo, we can spend a few moments here in our astronomy 1020 class as well, right? I think think about that. If that was worth their time, I'm walking on the moon. It's the first time you've ever done that. There's so much to see and look at and do. And he took 1 minute and 30 seconds to reproduce Galileo's experiment. That tells you about the psychic importance of this discovery of little g. Okay, let's talk about what else we've learned here during this exercise. We learned the units of acceleration and velocity are different, and that's going to come into play here, okay? So one of the takeaways that I wanted you guys to gather from this, and forgive me if it was a bit long-winded, is that when it comes down to units, both speed, comma, and velocity, they both have units of meters per second in the MKS system, whereas accelerations in the MKS system are meters per second squared. And that's something that you can easily forget if you're not being careful. Now that I've checked off these two background boxes, it's time for us to learn what Newton had to tell us about motion in the Principia Mathematica, okay? I found this lying around, discarded on a table on the second floor of CCRI. It was a great treasure. I felt like I had found a brick of gold, okay? And reading this old book, there's lots of funny things that he talks about in there. So at some point during this Principia Mathematica, Newton developed what are now known as Newton's 3 laws of motion. For newbie science students, try not to confuse Newton's 3 laws of motion with Kepler's 3 laws of planetary motion. There's going to be a bunch of these that get all mixed up in your head. All right, so the first law is called the law of inertia. And the law of inertia says that, an object in motion tends to stay in motion unless acted upon by an outside force. An object in motion tends to stay in motion unless acted upon by an outside force. The message here, the meaning, I can't even spell idea today. The idea behind this is that forces change velocities. That's the concept, that forces change the motion of bodies. There's a corollary to this, another way of stating this, sometimes phrased as an object at rest tends to stay at rest unless acted upon by an outside force. Why does such a law need to be stated? Because in Aristotle's original book on physics, he tried having a description of motion in which he talked about why objects like stones and rocks come to rest when they are rolled along the ground. So Aristotle had this idea that the Earth has some sort of magical pull at its center, and that all objects want to exist in a state of rest somewhere at the center of Earth. And this is what he called gravitas. It sounds trickily like Newton's gravity, but it's not the same thing. His idea that all objects were trying to return to the center of Earth, which was the primary center of the universe and the ultimate place of resting. And so his idea was, okay, so if you take a brick or a stone and you give it a little push and you push it on the ground, it'll roll for a while, but eventually it'll come to rest, because rest is the natural state of motion, because things want to fall to the Earth. So he had some kind of kooky things going on where things stop because they want to fall towards Earth, which if you even draw it out with arrows kind of seems weird. Newton realized that stones that roll along the ground are subject to other types of forces that people hadn't considered before, like, for instance, frictional forces, which are sideways forces acting between the stone and the ground. Newton realized that these frictional forces were resisting the motions of objects. And then he realized, what if you could take this eraser and you could put it into outer space, free of external media, nothing interacting with it? In that case, one single flick could get this thing traveling through space at a constant velocity, and there would be nothing to slow it down or to fight against its motion. In other words, Newton understood through his law of inertia, sorry, let me get rid of this, what most of us youngsters understand simply by playing the video game Asteroids. And if you've never played it, you can go to Free Play sometime, and they've got a copy of it there. And it's a jolly good time. You know, you have to rotate the ship around to shoot the asteroids, but if they get too close, you can fire your rockets, give the ship some thrust, and send it flying through space. But once it gets moving, it gets a little bit out of control. You have to sort of rotate it 180 degrees and fire the rockets again to slow it down. So these are things that we take for granted because we grew up with the law of inertia in science fiction movies and in fun video games like Asteroids. In, what was it, 1700s, Newton did not have asteroids at his local pizza parlor. He had to think up this stuff first, and that's an impressive feat, right? All right, so the first law tells us that forces change motion. But what is a force? That's where the second law comes in, which is the definition of force, the mathematical definition. And it's one of the most famous equations in all of physics. Force equals mass times acceleration. Now, we can derive the units of force by considering the units of mass and the units of acceleration. The units of force can be found by multiplying masses, kilograms, times accelerations, meters per second squared, and smushing them all into the same fraction. The way we say this is kilogram meters per second squared. If you want, you can say kilogram times meters per second squared. That's a little bit more of a mouthful. So people usually say kilogram meters per second squared. And we redefine the kilogram meter per second squared as 1 Newton of force. 1 N means 1 Newton of force. After dear old Sir Isaac, Newtons are also MKS units because they're derived in terms of MKS units. And a Newton of force is a kilogram meter per second squared. Okay. Obviously, it's a lot easier to say Newton than it is kilogram meter per second squared, which is why people rename units in such a fashion. Because I've got a lot to do today and not as much time as I would like, I'm going to get right on to the third law, and we'll come back to that later. You'll notice I'm not using quite as many slides today. That's because I'm trying to be efficient for once in my life. All right. I don't know what the title of the third law is. I've lost it, or it's been lost. Somebody knows what it is, but I don't know what it is. But I know the third law of motion. Newton's third law of motion says, for every action, and action is kind of an old-timey way of saying force, there is an equal but opposite reaction. And you could think of reaction as a counter force. I think the third law of motion of Newton's is the most mysterious and beguiling. And it's one that kind of shows up in all kinds of interesting and surprising places. The idea is that if you're exerting a force and you do not move or you do not change your motion, there have to be other secret hidden forces that spring up almost from nowhere. And this is why I like it so much. For instance, consider pressing your finger against the wall. You could push your finger against the wall, against a brick wall, and have nothing happen. But if you're exerting a force from your finger to the wall and you do not move, you do not begin to accelerate, then in a weird way, the wall must be exerting a secondary balancing force against your finger. And these two forces cancel out such that nothing happens. Another example would be the thrust of a rocket engine. By sending exhaust out the back pipe of the rocket, by creating a force that blasts behind you, the rocket pushes forward through space so that for every action, there is an equal and opposite reaction. Now, if you start thinking about that too hard, you start getting confused. And that's when you know that there's something cool going on, right? In any case, we're probably not going to make use of this too much. But as time goes on, I realize that this is one of the coolest of the three laws of motion, just because of its mysterious like nature.
That's kind of what, like, I don't really understand them, but like non-Newtonian fluids are like. Is that what they're referring to? Kind of.
Well, those laws apply to non-Newtonian fluids as well. And non-Newtonian fluids are cool because they act like solids or liquids depending upon the force that you exert on them, right? So if you hit them really hard and fast, they can recoil like a solid brick object. Whereas if you push through them slowly, they act more like water. Someone told me they're now making speed bumps from non-Newtonian fluids. I had never heard of this, but a friend of mine was having a discussion and said they're now making these speed bumps from non-Newtonian fluids so that if you are traveling really fast and your car tires hit them, they exert a counterforce and mess up your undercarriage. Whereas if you travel over them slowly, they just kind of squish under your tires and don't really scrape up the bottom of your car. I think that's a wild idea, but I have never seen such a thing. So I don't know if you guys have.
I haven't. That's interesting.
Yeah. But I guess you're kind of catching me on the spot. So I have to think, is there anything? Of course, this law will apply to non-Newtonian fluids as well as regular objects and regular fluids. But I'm having trouble of thinking of something specific to say about that.
It's fine. I just think it's weird, and I started thinking about that.
Well, now you've got me thinking about it, Ian, and I like the thought that you planted in my head. So I'm going to meditate on that, and at some point I'm going to have something profound to say. But right now it's eluding me because I feel like you might be onto something. There may be some cool connection between this law and non-Newtonian fluids. How do they? What I'm really thinking is, how do they work again? Like, there's some gaps in my knowledge of non-Newtonian fluids. Okay. All right. Though Newton's laws of motion are a science classic, you almost kind of have to talk about them before you can talk about anything else. For the most part, we're not going to use them too much, but we will use the things that come from them. For instance, we need to talk about the force of gravity in particular, and that's really important. It's also important to understand that forces make masses accelerate, okay? That's the concept. We've gotten to a good place, and we're not even close to tea break yet, which is great, because I have some problems, some math problems for us to do today. So with your kind permission, we will shift out of Newton's 3 laws of motion, and we will start to analyze Newton's law of gravity together, okay? All right. So one of the things that happens if you type Newton's hometown into Google, Isaac Newton lived around, I don't remember exactly when the Principia was published, but it's around 1700. And there was a pandemic going on in Isaac Newton's time. It was the bubonic plague. And just like what happened this year due to coronavirus, all of these people were getting ill in cities like London, and they didn't know why they were getting ill. They thought it was dirty air. That's where the nursery rhyme "Ring Around the Rosie" comes from. Everyone was sniffing flowers to avoid dirty air. But of course, it turned out that it was rats carrying this virus that was being transmitted to humans through mosquitoes. All of the students had to flee college and return home to the countryside so they wouldn't get this bubonic plague. And if you type Woolsthorpe, England, that's Newton's hometown, into Google, the first thing that usually comes up is Woolsthorpe Manor, which is Isaac Newton's ancestral home, which, I kid you not, still exists today. You can go and take a tour of it. Now, he did what many of you youngsters did, and actually many of us, everyone did during the coronavirus pandemic. They returned home and they sat around in their bedrooms and they did a whole lot of nothing, right? Except Newton brought with him his textbooks, and the textbooks that he brought with him were Kepler's Harmonious Mundi and Copernicus and Galileo, and he probably had some Aristotle and some other stuff in there too. And he sat around thinking deep thoughts. And at age, I don't know what it was, like maybe 21 or something, he developed all of these important concepts that revolutionized physics forever. In fact, in some of the pictures of Woolsthorpe, you can see an apple tree that still exists today in the front yard. And in one of his manuscripts, Newton writes that one day I was occasioned by the fall of an apple. So he watched an apple plop off the tree in the front yard. And he said, boy, that made a deep impression on me, because he realized that the same force that's pulling the apple to the ground must be the same force that holds the moon in its orbit. And this was, I believe, a eureka moment for him for the following reason. If you think about circular orbits, so let's go back a little bit. If you analyze them from Newton's laws of motion, at first they don't seem to make a whole lot of sense, because you have the moon. Let's see if I can do this in yellow. And the moon is traveling around Earth at the center in an almost perfectly circular orbit, and it has a velocity that's traveling to the right at the top. A few moments later, the moon moves in its orbit, and now it has a velocity that's pointing down in the picture. Velocities are speed plus direction. So even though the moon is maintaining a roughly constant speed, the direction of motion is changing, therefore the velocity is changing. But we know that changes in velocity are the same thing as accelerations. And we also know that accelerations are caused by forces. So Newton argues the only way the velocity can be changing as the moon goes in its circular orbit is if something keeps this thing from moving unless acted upon by an outside force. But where is the outside force? After much meditation, he finally realizes the force is centripetal. It's always pointing towards Earth. And by constantly pointing towards Earth, you get a combination of two motions. You get a combination of the downward acceleration of the moon, its initial sideways velocity, and the resulting motion is a combination of the two. It moves a little bit over to the side. Now, in the next frame, the object still has the sideways velocity because there were no sideways forces acting on it. It still has the downward acceleration. And once again, its motion is the combination of the two. He somehow realized that if there was a continuous force keeping the moon pointed towards Earth, that would explain its circular motion and relate it to the same forces that hold an apple to the ground. That's important because prior to Newton, prior maybe to Galileo, people believed that the forces which governed bodies on Earth were fundamentally different than the forces which governed the mystical heavens. That goes all the way back to Aristotle's primeval elements, right? Aristotle believed earth, wind, and water and fire were the substances of Earth, but that the substances of the heavens were this magical fifth element called ether. And the heavens were somehow perfect and magical, and they obeyed different laws or properties. By Newton realizing that something as dumb as an apple falling off the tree was related to the orbit of the moon, he basically connected the forces of nature from the quotidian to the universal, and that was pretty cool. At some point, he developed a mathematical formula for gravity, and he realized that it had to do with mass. So let's look at the way that Newton expressed it in the Principia. So this is what's now known as Newton's law of gravitation. But the way that Newton expressed it was in a somewhat primitive form to the way we do it now. He imagined that you had two massive bodies, sometimes called mass 1 and mass 2, and that the two massive bodies were separated by a center-to-center distance, little d. Newton wrote that the force of gravity is proportional to the product of the two masses and inversely proportional to the square of the distance. Well, we've used this little Jesus symbol for the first time here. This symbol means proportional to. The proportionality symbol is a powerful operator that lets you do things that an equals sign can't. The language is important here, so I want you to write down the language as well. In the top, we have proportional to the product of the masses. And at the bottom, we have inversely, I think there should be an E there, inversely proportional to the square, an underlined square of the distance. I think the language kind of matters here. The proportionality symbol will not let you calculate the magnitude of the force in newtons, but the proportionality symbol will tell you how forces will change when you modify some or all of these variables. And sometimes that can actually be a more powerful tool. This also suggests that any two objects with mass separated by some distance will have this magical force of gravity operating on them. And that's pretty funny if you think about it, because, well, things like apples and these two moonballs here, these two moonballs have a mass. The mass is probably 100 to 200 grams for each of these, is what I'm guessing. And they're separated by, I don't know, maybe 1/10 of a meter. There should be a force of gravity attracting these two objects. Gravity is always an attractional force. Of course, you cannot feel it because it turns out that gravity is a weak ass force. It is so weak that you need a tremendous amount of matter before dummies like us start to notice it. Okay, to find out if you guys understand how to use this proportionality symbol, because we're going to use that for our homework next time, let's try an example. We know that there exists a force of gravity between Earth and the moon. That's why the moon stays in orbit. What would happen if you were to double the mass of Earth and Moon, the question we would like to ask is, how would the force of gravity vary? So this is what you do with the proportionality argument. I'm expecting someone like Sage, who has some mathematics training, would know how to do this. I'd also expect that some of my 1010 students would know how to do this. So in other words, any single one of you better be able to do this. Okay, Ian, show us how it's done. How do we use that proportionality symbol? Let's show our less experienced students how it's done.
You're killing me. Okay. So sorry, I'm just.
All right, Ian, let me give you a hint.
I know you want to plug stuff in. I'm trying to remember.
Well, what you're supposed to do with the proportionality symbol is you start by ignoring things that are not varying. So
Yes.
what quantities are not varying?
Distance is not going to change.
So let's forget about the distance and let's rewrite the expression is the force is proportional to the product of the masses.
Oh, you know what the reason I started feeling weird is because I started thinking like, oh, I don't remember what like the masses are. No, but
you don't need to know the masses. That's
yeah,
the whole
exactly.
beauty
It
of the proportionality.
just clicked in my brain.
It doesn't matter what, suppose we doubled the mass of hoo-ha and doodah. It doesn't matter, right?
So it would be 2 times 2 for the masses, right? Because they're both
Right,
double.
because both of these are varying by a proportionality factor of 2. Now, as soon as I put in the proportionality factors, it's now become a math problem.
Yep.
And 2 times 2 is 4. 4 times stronger. Okay. Sage, why don't you take us out with the next one? I just want to make sure you guys remember how this is done, okay? So let's call that example 1. And this matters because it's going to come up in our class from time to time. So Sage, let's try example 2. What happens if I double the distance?
The gravitational force will halve.
False. Let's do it slower this time, Sage.
Okay.
What is the proportionality argument? The force is proportional to what?
The mass times mass over.
No. You're already doing it wrong. When I double or change some or any of the quantities, the first thing I should do is rewrite the proportionality argument, omitting and removing all quantities that have not varied.
1 over d squared.
That's what I want to hear. Okay.
Yep.
Force is inversely proportional to the square of the distance. And now what do I do?
That'll be 1 over 2 squared, so it's a fourth.
1 over 2. So it's not that you half the gravity.
Yeah, it's that you're 1/4ing. I don't know
Right.
what the nomenclature for that would be, but
Well, you could say the new force is 1/4 as powerful,
yeah.
or you could say the force is 4 times weaker, right? You could say it in one of 2 ways. Saying the new force is 1/4 the old force is a bit eggheady and not smooth. Saying the new force is 4 times weaker is a smoother way to say that. You've reduced the force by a factor of 4. Okay, I hope through those 2 exercises that Sage and Ian eventually bungled their way through, and you did it successfully, guys. So, pat yourselves not too intently on the back, okay? That this is how we use proportionality arguments. I'm worried about students who have never seen this before, is that you just kind of remove the things that don't vary, and then you plug in the factors by which those things vary, and you see how the force changes. We're going to be doing this in our homework on Tuesday, so that's why we had this talk. You might wonder why Newton stopped there. Newton stopped there because gravity is so weak that he didn't have a way to measure or quantify this force. And a way to really help you understand the problem is to think about this whole argument in terms of units. And do you guys mind if I erase my 2 examples here? Is that okay? All right. I want you guys to go on a little imagination trip with me for a second. If Newton wanted to investigate this force, he'd have to consider measuring these quantities in some particular unit system. Let's say Newton decided to use the MKS system, which he probably did not, because I don't think metrics had been invented then. In the MKS system, masses should be measured in units of kilograms, right? And what should distances be measured in?
Sorry, meters.
Right. So let me write this in a different way. So on the top, we have some number of kilograms times some number of kilograms. On the bottom, we have some meters squared. And what units should we use for forces?
Newtons or kilogram meters per second squared.
Right. And now you're starting to see the issue here. There's actually two issues, and it's the same issue, but I want to present it from two totally different weird points of view. In one sense, the units here do not match the units there, and that's a problem from a science perspective. In a philosophical sense, kilograms, I usually have a show and tell for my students with kilograms. I like to think of a kilogram as just the kind of thing I wouldn't want dropped in my head. It's roughly got the heft of a brick, okay? And so, nature doesn't know anything about kilograms. This is a human-invented imposition on nature. We decided that this quantity mass, the stuff that's the stuff within stuff, we should be measured in units of about yay much, and we just made it up. Likewise, nature doesn't have a conception of meters. Nature might understand distance, but we imposed upon nature that this should be the gold standard, the increment by which we measure these things. And because we also invented seconds, not only did we invent kilograms, not only did we invent meters, but we also kind of invented newtons because we invented kilograms, meters, and seconds. All of these units, all of these measurements are human-based conception. At some point, see, gravity is not a human-invented conception. Gravity has just been there since the beginning of time. It's embedded into the gameplay of the universe. At some point, we have to ask nature what she thinks about gravity. By the way, nature, if I have two 1 kilogram masses and I separate them by 1 meter, how hard do you plan on tugging those two things together? That is not up to us. And that's why there needs to be another quantity to turn this into an equal sign. That quantity will be a measurement of the strength of gravity, and it will be nature telling us two 1 kilogram masses separated by 1 meter will tug each other this hard. And that quantity is called big G, the universal gravitational constant. It's probably your first constant of nature. Introducing the universal gravitational constant, otherwise known as big G. It's a tiny little number, approximately 7 times 10 to the minus 11. Its units are a bit weird. Meters cubed per kilogram per second squared. This number is the same all across the universe. You can think of this number as an index of the strength of gravity. To be honest, folks, my history is a little bit rusty. I think because Newton was such a genius at mathematics, he probably understood that he needed a number like this to turn his proportionality into an equal sign. But Newton would have had no way of knowing how to discover this or to measure it. And that's because, and he probably tried to do an experiment similar to this, if you take several kilogram objects and you separate them by a short little distance like 1 meter, you won't notice any tug between them and you won't be able to perform the experiment. Except if you're a real badass like Henry Cavendish was maybe 100 years later, you'd keep trying until you actually did find it. Let me tell you about the man who turned the proportionality symbol into an equal sign. His name is Henry Cavendish, and he performed a legendary experiment called the Cavendish experiment. Now, kind of a funny story here. The Cavendish experiment was, he took these two giant lead spheres, maybe roughly the size of bowling balls made of lead, and he suspended them from this very delicate twisting balance beam that's called a torsional balance beam. And let me show you a more abstract picture here that might help you understand how this works. He essentially took two large spheres. This is actually a decent picture. This is a decent picture here. Let's go with this one. Sorry, guys. Let's go with this one. I just want to find one that's easy to look at. All right. Control minus, let's get down to 100%. Okay. So he has these really intense lead spheres. They're big, they're massive, they're heavy. And then he fixes them on this sort of platform, and he suspends these smaller spheres on a very thin quartz fiber. This is called a torsional balance beam. It can rotate side to side if it's delicate and imbalanced, but it won't move up and down. And then he suspended this rod such that the spheres were a short distance away from the larger spheres, and he got it so perfectly balanced that even the slightest little deflection could be measured. And here's the genius of geometry coming into play. The spheres did exert some gravity on the smaller spheres, and they gave it the most microscopic of little tugs. But he could measure this microscopic tug because you can shine a laser onto a mirror, and even if the deflection is microscopic, the laser, as it travels farther and farther away from the experimental apparatus, the beam will separate more and more. And using basic geometry, you then go and you measure this angle, and the small angle formula lets you calculate the force. Freaking genius, right? So even though the deflection was so microscopic, he could use the fact that two beams will diverge over time to turn it into a geometry problem. What a clever person. By the way, I don't think he understood fully the significance of what he was doing, because the research paper that he published in the science articles, the title of it was "On a New Method of Determining the Mass of Earth." So he wasn't even so much thinking that the big importance of what he was doing was measuring big G. He thought that what was cool is he could now calculate the mass of Earth from it. And okay, fine, but why are you messing around with Earth when you just discovered the internal machinery of the physics of the universe, right? So, okay, now that we understand what big G is all about, and we understood that it took several years after Newton to figure this out through artificers, okay, we now have arrived at the proper modern version of the law of gravitation, which we're going to try out before tea break. And the modern law is that the force of gravity is equal to big G times m1 times m2 divided by the distance squared. This is our bad boy here, all right? Once again, the fact that it's a law, if you guys know anything about science philosophy, laws are useful rules in physics that are essentially lies. And this is not perfectly true, but it's useful in 99.9% of situations. Why don't we try a sample problem, and let's find the force of gravity between Earth and the moon, something that Newton probably would have enjoyed doing. So example question 1. Find the force of gravity between Earth and the moon. All right, we're going to need some data to do this problem. We know big G is 7 times 10 to the minus 11 meters cubed per kilogram per second squared. That's a constant of nature. It never changes. However, now we're dealing with particular masses. The mass of Earth is 6 times 10 to the 24 kilograms. Thank you, Henry Cavendish. Okay. The mass of the moon is 7 times 10 to the 22 kilograms. I don't know who first measured that, but I have thought about how they did it. And the distance from Earth to moon is 384,000 kilometers. All right, students, you are all experienced men of science. I suppose we have, this is resembling one of those old-fashioned physics lectures where it's just the gentlemen sitting around having a discussion. Sorry, ladies, you got to join the party, all right, if you want to come do physics. Well, how should we begin this problem, gentlemen?
Probably replace the variables and then multiply the top together.
That would be an error, Sage. You will have failed to account for one eensy-weensy little detail that's going to throw the whole thing off. Eventually, Sage, we do want to do what you said, but there's a pregame step. We got to pregame this.
Let's do some units.
Yeah, let's deal with some units.
Cool.
What units do we want for masses and what units do we want for distance? Let's think about that.
We
Masses-
want, oh, I'm sorry.
No, please go.
Oh, kilograms for mass, and we're gonna go with kilometers for distance, or meters for distance. Sorry.
Like MKS. One of the troubles with the MKS system is people keep thinking the K means kilometers. The K means kilograms.
Got you.
The M is for meters. In other words, to spell this out for students who don't do this very often, the kilograms are cool in their current form, but the kilometers are an issue. What are we going to do about that, Sage?
Let's believe divide by 1,000.
Whoa, 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 whoa.
No, you can
Dimensional analysis.
Let's do some units. Okay,
Okay.
so let's start with kilometers and multiply by a times sign.
By a division bar, okay.
Or,
Like that. Units first, Sage.
yeah, let's go with kilometers on the bottom, meters on the top.
All right, and now we can put the numbers in last.
Okay, let's put 1,000 up top and 1 on the bottom.
Do you see how that's better than thinking, wait, do I multiply or do I divide? You let the units tell you what to do, Sage.
Yeah.
Okay, Sage, I bet you're so good at math that you could do this right in your head. No calculators needed. How many zeros do you have there?
We have 6.
So
Sorry, same
can
pattern
you
though.
imagine a cool way to write that in scientific notation?
Yeah, 384 times 10 to the 6
Meters, nice.
meters.
So 384 million meters. For students watching at home in the television show, we have just converted our distance into meters, and that's what the formula requires in order for it to work. All right. I've kind of gotten too low to the bottom, so I have to erase this in a second, and we'll plug it all in. Sage, do you have this copied down?
I was switching my headphones.
I
I
think-
didn't hear you.
I think Ryan Spaveled fell asleep, but I don't blame him. He's seen this stuff before. That's okay, buddy. I've fallen asleep in quite a few lectures. I once was in this math lecture and I fell asleep like this, probably because I'd been up too late. And the math teacher had to wake me up. The professor woke me up in the middle of class because he was like, Brennan, we're just worried that you're going to hurt your neck.
No, I'm not asleep.
My-
It's just my eyes are not very open that much
you
right now.
just resting your eyes. Huh? Is that what it is?
No, it's just I've been squinting a lot and not. I'm still looking at you.
All right, I'm just teasing you, Ryan. I know you've done this stuff before, so I'm just teasing you.
Just as a fun aside, my brother told me a story one time where he fell asleep in a lecture in college and woke up in another class. And he was like, "Where am I? Who are these people?" And he just walked out.
They have this legendary story about the physicist Richard Feynman, who went to see, professors give visiting lectures to each other. And Feynman went to see this physics lecture by another famous physicist, and he immediately fell asleep in the lecture. And then at the end of the talk, he had missed the whole thing. He woke up at the very end and he asked the speaker a question. He said, your quantity there, the units don't balance out, so none of this makes any sense. And the guy was completely humiliated, and everyone realized that Feynman had been right. So if you're Richard Feynman, you're allowed to sleep through physics lectures. Otherwise, okay. So remember what we were doing here. For question 1, we are trying to find the force of gravity between Earth and the moon. In the previous problem, we had gotten all of our units into the right step, and now we're going to sort of write it out. So the Earth to moon gravity, force EM, I'll do E plus M. I don't want to confuse it with electromagnetism. First, we'll put in big G, which is 7 times 10 to the negative 11. I want you guys to carefully watch how I write this stuff. I'm going to put in my units along with the numbers when I set this up. I expect you all to do the same on your homeworks, or I will delete points, okay? So we have meters cubed per kilogram per second squared times big G, 6 times 10, times the mass of Earth. That's big G, that's the mass of Earth, times the mass of the moon, 7 times 10 to the 22 kilograms. And that's all divided by, watch how I write this and do after me, 384 million meters, close parentheses, squared. A lot of people who see me put those parentheses in there, they think I'm doing that for the calculator or for order of operations. In fact, when we plug this into our calculator, we will not need to use parentheses at all. The parentheses are there for bookkeeping because the square must be distributed not only to the number 384 million, but the square must also be distributed to the units of meters. If you don't put the parentheses there, one could easily mistake this for 384 million square meters, and then you would forget to square the number. It sounds kooky, but it's good logic, okay? Now, this is not a difficult problem to plug into your calculator, but some of you, actually all of you are probably going to be comfortable with this. I think there's going to be people watching at home for the first time who think this is nuts. So I know Ian, Ryan, and Ryan can do this because they've been trained. Sage, can you do this? Do you know how to punch this in? All right, yeah, he's child's play, he says. Okay.
No, I just, maybe, probably. Let's find out.
Let's find out. I'm eventually going to show everyone at home, but I wanted to see if you could get it first.
Let's see.
What's that cat's name, Ian?
His name is Zeus.
Zeus.
Zeus. I love that.
And he's part Russian blue, and he like imprinted on me, so he follows me everywhere. He won't let me alone.
That's cool.
So how many sig figs do we want?
2.
Just one?
When in doubt, choose 2.
Okay. So let's do 2.0 times 10 to the 20th.
Yes, he got it right. Okay. And I expect Ian, Ryan, and Ryan to get the same thing. This now is not so much for you guys, is for the studio audience at home who may not have the same chops that you guys do. Okay. So do this in memory of me. Okay, let me get the right distance here. Okay. First, we'll do big G, 7 exp negative key 11 times the mass of Earth, 6 exp 24 times the mass of the moon, 7 exp 22, divided by the distance, 384 exp 6. We have to square the distance here. So I hit the square key, whoop, and then we hit equals, because when you hit the square key, that just shows you the distance squared. And the final result is 2 times 10 to the 20th. Sage, what are the units of this force? Sage?
I was just kind of thinking about that for a second. I felt like it should be, okay. Let's go with mass times kilograms over second squared. Maybe.
Yeah.
Yes, okay.
Oh, not mass. Don't say mass, it's meters.
I'm sorry.
So meters squared cancel 2 of the meters. You have 1 meter. 1 kilogram cancels out. You have 1 kilogram. And the second squared stay in the bottom. Kilograms times meters per second squared. Also known as a...
Newton.
That's
Newton?
right. It's a
Cool.
force. And the MKS units of force are newtons.
Cool.
So if you balance the units the way that Sage did, he naturally discovered the units are newtons because he got meter times kilogram over second squared. A moment ago, we defined that as a newton. Okay, that is certainly a big number of newtons. Let's compare it to something in our everyday lives. Class, this is a 1 kilogram mass. If I hold it in Earth's gravitational field, it exerts a force on my finger. You can see it bending my finger. It kind of hurts, actually. How many newtons are being exerted on my finger right now? You should be able to do this in your head. How many newtons? Let's think through it together, gentlemen. What is Newton's second law of motion? Someone talk to me. Ryan Dick.
Force equals mass times acceleration.
Ryan Dick, what is the mass?
1 kilogram.
What is the acceleration, Ryan Dick, of Earth's gravity?
10.
So what's the force exerted in my finger right now?
10.
10 what?
Meters per second squared.
No, that's an acceleration. Okay, we
In
have
newtons.
shit. Oh, say that?
Newtons.
That's right.
Yeah, it's a force.
This force, the force of a brick in your hand, is 10 newtons. How does that compare to the force between the Earth and the Moon?
It is very, very small.
This is a 2. If you divide the 2, if you divide this by 10, you get a 2 followed by 19 zeros, right?
Yeah.
There are names for big numbers like that. Do you guys know about this? The names of big numbers. We'll occasionally want to look at this in our class. Names of big, I want to get better at learning the names of big numbers. So
Okay.
I'm secretly working this into my lectures so that I can train, okay?
I know up to quadrillion,
Say that again?
but I know up to quadrillion off the top of my head.
Okay, so quadrillion is 10 to the 15. So let's do this in terms of 10 to the 18.
Yeah, you
So-
get picking like
Oh, it's, sorry, I was going to say 10 quintillion times greater. The force of gravity between Earth and the Moon is 10 quintillion times greater than the tug of this kilogram against my finger.
It's so large, it's not. You can't even comprehend that.
Yeah, I think the number of seconds since the Big Bang is 10 to the 22, right? So these are quite impressive numbers. Class, do you remember what's stronger, the force of gravity between Earth and Moon, or the force of gravity between Earth and the Sun?
I'm gonna guess the sun.
The moon.
Oh,
All I remember is that last semester you asked this, and I remember it being a trick question because I thought it was one thing, and then it
no
definitely.
tricks. It's either Earth-Moon gravity or it's Earth-Sun gravity. It's not a trick. It's a test your science intuition question.
Yeah.
All right. Sage has a vote for Sun-Earth gravity being stronger, and Ian has a vote for Earth-Moon gravity being
Well,
stronger.
you know what? Let me explain my thought here.
Okay.
You did something a second ago where we were talking about if the distance between the Earth and the Moon was like way greater, then the force between them was way smaller.
So this is actually why it's hard to guess, because the Moon is less massive, but it's a lot closer than the Sun. So it's not obvious right off the bat if the mass or the distance is going to beat the other one out. So it's actually a pretty reasonable guess on either side. Luckily, we have Newton's law of gravitation, and we can calculate it. So this gravity here is the Earth-Moon gravity. Now we're going to try to calculate the Earth to Sun gravity. So let's do Sun and Earth force of gravity. To do this problem, we're going to need the mass of the Sun, which is 2 times 10 to the 30 kilograms, I'm going to skip doing the units and colors because I can move a little faster. What is the distance between Earth and the sun? You're supposed to know that.
1 AU.
How many kilometers is that, Ryan? Traveled. I think that's
150 times 10 to the 6th, I'm pretty sure.
nice. And how many meters is that? Even if you can guess, Ryan, let's do a dimensional analysis for any of the students watching at home, okay? We start with the number we want to convert, 150 million kilometers. Now we multiply by a division bar. Ryan Spavel's, give me the units.
You'd put kilometers on bottom and meters on top.
Okay,
1,000 meters equals 1 kilometer, so 1,000 on top, 1 on bottom.
okay, kilometers cancel. And then how should we express this most elegantly?
Just it'd be 150 times 10 to the 9th.
Yeah, 6 zeros, 7, 8, 9 zeros. Nicely done. That's 150 billion meters. Let's set up the equation. Force of gravity between sun and earth. So first we're going to have big G, 7 times 10 to the negative 11 meters cubed per kilogram per second squared, times the mass of the sun, 2 times 10 to the 30 kilograms, times 6 times 10 to the 24 kilograms, divided by 150 billion meters squared. Okay, kids at home, try this on your calculator and see what you get. If you're watching at home, you should have seen me plug this in, use the same method, punch it again. Someone just shout the, I want to move faster now, so someone just shout that answer.
I got 3.7 times 10 to the 22nd.
And if we want to round it really crudely, let's just say 4 times 10 to the 22nd in the units.
Newtons.
Once again. So Ian, what did you learn from this exercise?
Exactly what I remember happening last semester as well. Is I guess the
got
moon, and
tricked.
then we did this, and then the sun had more. So
See that, guys? I tricked Ian again. Even though I said I wasn't going to trick him, I tricked
yeah, every time.
him. You know, I have this joke that I like to make about teaching, having done it now for 10 years. And my idea of teaching is like this. You set up this elaborate trap for your students, right? Like you put them in a room and you make them walk across the room and you put a banana peel in the center of the room. And then what you do is once you've set up the banana peel, you stand next to the student pointing at them and you say, don't slip on the banana peel, don't slip on the banana peel, don't slip on the banana peel. But of course, they're not going to listen to you. So what do? Whoop, they slip on the banana peel and they bonk themselves on the head. And that's when learning begins.
I thought it was going to be more like you put the banana peel in the room, you don't tell them about it, they slip on it, and you say, see, you can learn from that.
It doesn't matter, though, if you tell them or if you don't tell them. People just don't like to listen. And I include myself in this people here. It's hard to listen and take advice from others. Okay, so Ian discovered that the force of gravity between the sun and the moon, the force of gravity between the sun and the earth is stronger than the force of gravity between earth and the moon because the sun's mass totally wins out. It's a 2 followed by 30 zeros. How many times stronger is, let me set this up the way the book is going to do it, and then we'll take a tea break. I'm going to erase all this, guys, okay? One thing that you'll often see during our homeworks is people will ask you to compare the force of gravity between, say, sun and earth to the force of gravity between earth and moon. And do you guys remember what compare means in this class? Shit, that's why we're doing this. Compare means you take the ratio. Remember that. Compare means you take the ratio. So we're going to divide 4 times 10 to the 22 newtons by 2 times 10 to the 20 newtons. Okay, Ian, explain to the studio audience at home how you do that without a calculator.
You can subtract the exponents. So you get 10 times 10 to the second, and then 4 divided by 2 is 2.
So the lead digits, 4 over 2 gives you 2 times 10 to the 22 minus 20 is 2. The newtons cancel out. What's that number?
That means it's that many times.
What is that?
Difference.
What is that?
I'm like 200. It's 200 times greater. I don't know.
Yeah.
I'm used to looking at 3s and 6s. For some reason, I saw the 2 in my brain.
The sun's gravity is 200 times stronger than the moon's gravity. On Earth. The sun's gravity is 200 times stronger on the Earth than the moon. And yet, my friends, it is the moon that is responsible. Where are we here? Come back to this stuff later. It's the moon that's responsible for tides. Isn't it funny that the moon causes tides when its gravity is 200 times weaker than the sun's? We can discuss that after a little tea break, okay? So I went a little bit late here. That's okay. I was doing something. We were all doing something. I'm going to set the top stopwatch for 25 minutes as usual. And after 25 minutes, we'll come back. Ooh, that's a cool effect. After 25 minutes, we'll come back and we will resume our lecture. Sound like a plan? We are going to do a short, simple, but instructive lab today, calculating the period of the ISS. So you don't need to print out anything for today's lab. We're just going to do it all on paper, okay? It'll be great. So I'm starting the timer. I'll see you guys in 25 minutes. Okay, friends, back from our little tea break there. And now that we've learned a little bit about how to calculate forces of gravity. Oh, Ian, before you left, I just wanted to say that on Tuesday, we'll resume our regular homework schedule.
Okay. Cool.
So meet at 10. So that's what you missed.
Okay, because I heard you go, oh, wait, and then it was too late. All right.
All right.
Bye.
Bye, Ian. Okay. I'd like to see if we can knock out 2 things before our lab. First is a quick, hopefully quick discussion of tides. The second would be something called Newton's interpretation of Kepler's laws. That's where the real meat and potatoes of today's lecture is. We do have a question for our homework on Tuesday on tides. So let's see if I can sort of get into this. So the way I like to set up the conundrum with you guys is to have you think about what's the cause of tides. We live in the ocean state, and most of us know that tides are related to the cycle of the moon. And we get 2 high tides and 2 low tides every day. There's a high tide that's roughly in the direction of the moon. And there's also a high tide that occurs opposite the moon as well. The low tides occur at 90-degree angles to the position of the moon. Of course, it's not magic that causes tides, it's gravity. But we saw before tea break that the gravity of the sun is 200 times stronger on Earth than the moon. How can it be that the moon is causing tides when its gravity is so much wimpier? Or rather, why isn't the sun the cause of tides? The answer has to do, believe it or not, Sage, with calculus and with the fact that the tidal force is not the same thing as the gravitational force, although they're related to each other. Let's take some notes and see if I can make this clear and plain. Okay. So for starters, let's try the following bullet points. Tides are caused by gravity. But, ... the so-called tidal force is not the same as the gravitational force. They're not the exact same thing. To spell it out clearly, the tidal force is a differential force. And I want us to underline the term differential force. That's a key phrase there. The tidal force is a differential force caused by gravity acting over an extended body. In other words, if you want to talk about a differential force, the tidal force in some ways is a delta force. And I ain't talking that Chuck Norris movie. I'm talking calculus, okay? A differential force in some simple basic astronomy 101 way means the difference in force between the force acting on the front of an object versus the force acting on the back of an object. Now, you folks have noticed that I'm taking special pleasure with Sage in my class only because it's so rare these days to have a student majoring in mathematics. That's a treat for me. I get to tickle him and tantalize him with stories of calculus. For anyone out there in the studio audience, and there are some students of mine that occasionally have had a little more math chops, the tidal force is the derivative of the force, which, if you know anything about calculus, is sort of the same thing as a change in force from front to back. What's interesting about the tidal force from a mathematical perspective, and I want to tell you that this ties into our earlier lecture on proportionality symbols. Whereas the force of gravity is proportional to 1 over the distance squared, in a screwy way, when you take the difference of force from front to back, the tidal force is not proportional to 1 over d squared, but the tidal force is proportional to 1 over the distance cubed. And Sage, that ought to make sense to you, because you know if you take the derivative of 1 over d squared, you end up with a 1 over d cubed, right? But think about what that means. It means that tides get stronger closer to an object, and they enhance themselves faster than the gravitational force, but they get weaker as you get farther away. Tidal forces have a different distance dependency than gravitational forces. Okay, that's fun if you're Sage, but what about the rest of us? For the rest of us, maybe a cartoon would be helpful to explain this, and it might even be helpful for people like Sage too. Have you guys got all this? Okay.
Wait, why is there no 2 anywhere in there?
Because it's a proportionality symbol and constants are boring and they're for weenies.
Okay.
Right?
Okay.
We're interested in variables, bro. Keep the constants to yourself, okay? I mean, am I not wrong? That's the idea behind proportionality symbols, right?
No, absolutely. That makes sense. I was just wondering, I was thinking about derivatives.
You were actually trying to take the derivative and you were getting jittery. Well, I got to tell you, there's some other stuff that's being hidden by that proportionality symbol too. Be careful, you know, be careful. Don't open that closet, Blackbeard. You might find something you didn't want to see. All right. I'm going to erase this real quick. Because that stuff probably sounded a bit eggheady and confusing to people, why don't we do this in cartoon form, okay? You know, and in fact, I have a couple of stories to tell you that relate to other things I want to discuss in this class. Sorry, I'm just trying to drink this coffee before it gets cold because I love legal drugs. Okay. Now listen, when we calculated the force of gravity between the Earth and the Moon, in a sense, what we did is we treated both objects as if they were point particles that had 0 dimension and were separated by a distance of 384,000 kilometers. And in fact, when you're doing the law of gravitation, that's okay, because Isaac Newton made an important discovery when he studied gravitational forces. you will remember from an earlier moment in my lecture that I discussed Aristotle, and Aristotle's version of gravitas was that he believed all objects would attract and fall towards the center of Earth, which he imagined to be the center of the universe. And he imagined that that center of Earth was the ultimate resting place. I don't know what they called it, the prime mover or something like that. Now, when Newton started using his law of gravitation, he got a little bit nervous about this because Newton realized that the problem was more complicated and that Earth was made up of a whole bunch of different chunks of matter. After all, there's granite and rock underneath your feet that has mass. There's iron in the core. Shouldn't a man feel gravitational forces from all the little rocky, metally bits of Earth? Shouldn't he feel a gravitational force, for instance, that's tugging him over here from that little hunk, and then a force of gravity between the man and some hunks of rock over there? Shouldn't the man be subjected to all of these forces of all the different chunks of matter? So here's what Newton did to solve this problem. He invented calculus. And he invented calculus specifically so that he could chop the Earth up into an infinity number of little tiny mass bits and simultaneously calculate the force of gravity between the man and all the little chunks of mass. And here's the mind-blowing thing about what he discovered. By the way, basic physics students at a 200 or 300 level have to do this problem, and it takes a couple hours. It's tricky your first time around. And Sage may have done this before. When you actually analyze the problem, the most amazing thing about it is that he discovered that Aristotle was right. In actuality, the man does feel a force of gravity pulling him exactly towards the center because the Earth is a sphere that has symmetry. And for every chunk of mass that you have on the right-hand side of Earth, there is another symmetrical chunk of mass on the left-hand side of Earth. And what happens is, if the man feels forces from those symmetrical chunks, there are two components. There's a side-to-side component, which perfectly cancels out, and there's a downward component, which add to each other and enhance each other. So that ultimately, the problem of a man feeling gravitation from Earth is completely equivalent to a man standing on an empty soap bubble with a black hole in the center of the bubble, a point particle whose mass is equivalent to Earth. In other words, for all intents and purposes, you feel the exact same gravitational force as if you were standing on a hollow shell with just a single dot in the center, 1 Earth radius away, but whose mass was that of Earth. In other words, for once, Aristotle had actually been right about his intuition, and Newton went through a lot of work to prove this. However, just because that works, oh, by the way, short side note, there's another associated problem that sometimes intro physics students have to do. It's kind of cute. And that's of the astronaut inside of a hollow planet. If you carve out a hole or a sphere in the center of Earth and put a man inside of it, he will actually float weightless because of the spherical symmetry. For every chunk of mass on one side, there's an equal chunk of mass on the other side. All the gravitational forces cancel out. And if you could really journey to the center of Earth, as Jules Verne did in his ridiculous book, you wouldn't find dinosaurs there. First of all, you'd find molten metal. But second of all, you would actually float weightless in the interior of Earth because all of the gravity spherically surrounding you would cancel itself out. That's kind of wild to think about, right? Even though the man acts as if he's concentrated at the center of Earth, that gravity, it's not the same when you analyze the Earth and the Moon. And let's take a quick look at why. To do this right, I'm going to use some nice perfect spheres. So make a sphere represent Earth. This is really turning into a crummy lecture. Okay, so Anne, let's make a sphere to represent the Moon. And let's draw the distance between them center to center. And humor me if you will, guys. I like nice, neat diagrams. The radius of Earth is 6,400 kilometers. The distance to the moon, 384,000 kilometers. 6 times 2 is 12. The diameter of Earth is 12,800 kilometers. The first issue is that if Earth and moon attract each other gravitationally, the Earth's girth is an actual reasonable fraction of the distance between the Earth and the moon. And let's calculate it. What percent of the distance to the moon is Earth's diameter? 12,800 kilometers divided by 384,000 kilometers. Someone type that into your calculator and tell me what you get. Quick like a bunny now.
It's a third, isn't it?
No.
No.
You want to get fired?
0.03. Yeah.
Thank you.
Sorry.
Okay, what is that as a percentage,
Definitely
Sage?
wrong. That's going to be 3.3%.
3%.
Yeah.
So what this means is that the front of Earth is 3% closer to the moon than the back of Earth. Right, Sage? Imagine that I could take a planetary-sized cheese grater and slice the Earth up into thin slices of provolone cheese, except they were made of Earth rock. And I'm going to take a thin slice at the front of Earth, and I'm going to take an identically thin slice at the back of Earth. Roughly speaking, it's fair to say that the front slice of Earth is 3% closer to the moon than the back slice of Earth. And both of those slices have some small mass associated with them. If I calculate the force of gravity, the force exerted on the front slice of Earth will be stronger than the force exerted on the back side of Earth. By what factor? Let's argue it, Sage. If the front slice is 3% closer than the back slice, what percent will the gravity be different?
I want to guess 3%.
But it's not inverse square. It's inverse. Sorry, it's not inverse to the distance. Is inverse squared, right?
Okay, so that'd be 9.
Isn't that funny? It actually ends up being 9% stronger in gravity from the front of the Earth to the back of the Earth because of the inverse square proportionality. So what you get then is that the Earth is feeling a stronger tug from the front than it is from the back. If you're the Earth, what you're experiencing is a differential force. This force manifests itself as a side-to-side force that pulls and stretches out the Earth. All you know is this side gets tugged on harder than the back side, so you feel like you're being yanked apart. This is how we end up with our 2 high tides, right? The front side of Earth gets stretched towards the moon, but the back side's also being stretched by an equal amount. Another way to think about it is you can think of the center of Earth as being pulled away from the water. That's another way to think about it. In any case, you end up with 2 high tides aligned with the moon and 2 low tides which are being squished and compressed. I should also mention that not only do the oceans bulge in the direction of the moon, the atmosphere distends into the moon's direction, and even the ground rock underneath your feet deforms every day by roughly 3 centimeters in the direction of the moon. And it actually deforms Earth's shape from a perfect sphere into what we call an oblate spheroid, a slight bulge close to the equator. In some places in our solar system, that tidal bulge can become so pronounced that it can trigger volcanism and stuff, like on the moon Io. That's a story from my other class. Okay, so what we see then, and let's put some numbers on it. If Earth's getting tugged on the front by 40 newtons and on the back by 20 newtons, Earth will feel a differential force of 40 minus 20, or 20 newtons differential. And that's the tidal force. Suppose you were a pesky student and you said, okay, bro, but doesn't the sun's gravity exert 200 times more strength? Shouldn't it also exert one of these differential forces? The answer is yes, but consider the Earth's diameter as a fraction of the sun's distance. The distance to the sun is 1 AU, or 150 million kilometers, right? What percentage of the Earth-Sun distance is the diameter of Earth? The percentage of the distance would be 12,800 kilometers over 150 million. What does that get us, Sage?
8.5 times 10 to the negative fifth, which is like tiny.
9 times 10 to the minus 5 is 9 times 10 to the minus 3%, which is that's basically 9 thousandths of 1%. And so what's happening is, even if the sun exerts more force at all points on the Earth, the difference in force ends up being smaller because, for instance, it's like saying in a cartoon form that the front side of Earth might experience a force of 400 newtons, but the back side of Earth might experience 399 newtons. So the difference in force that the sun exerts is only a 1 Newton differential. Thus, it's possible to say two things that sound contradictory. The sun's gravity is at all points on the Earth stronger than the moon's gravity, but the difference in force that the moon exerts front to back is larger than the difference in force exerted by the sun. It's about whether your diameter is a large percentage of that distance. This is one of the reasons why black holes are so dangerous. Black holes concentrate mass into essentially a microscopic point particle. If your size is 0 dimensions, then anything right down to a kitty or a candy bar or even a human has an infinitely bigger length or diameter than the black hole. And as you get stupidly close to it, the tidal forces just go ballistic, right? Far away from the black hole, they just act like normal gravitational objects. But that 1/d cubed dependency makes them icky if you get too close. Okay, by the way, as any good cawhogger or fisherman in Rhode Island must know, the sun does contribute to tides. And in fact, there are things called spring tides twice a month, where during the new or full moons, the sun's gravity enhances the tidal force a bit to make stronger than usual tides. Twice a month, we also experience neap tides at first and third quarter moons, where the sun exerts a perpendicular gravitational force, which mitigates the tidal force. So tides are actually complicated because of the sun. And then there are local geographical factors, which I won't even bother getting into. Tides play a huge role in astronomy. And in this class, they're going to come up. That's why we had to talk about them. Module complete. Okay. Let's see if I can grab one more thing out of today's lecture. And it's kind of a big thing. It's sort of one of the major points of this entire lecture. Newton discovered newfound powers because he had developed 3 laws of motion, then he had developed the law of gravity, and he'd also developed calculus. And he found that if he smushed all those things together, he could make a diabolical math machine that would allow him to discover new truths about gravity, orbits, and physics. In particular, one thing that interested Newton was Newton did a new analysis of Kepler's 3 laws of planetary motion. Now, I had a really cool intro and setup to this that I don't think I have time for. Maybe I'll do it at the beginning of next class instead. I want to basically talk about how Newton reanalyzed Kepler's laws and what things he discovered from them. So instead of calling this Kepler's first law, I'm going to refer to this as Newton's version of Kepler's first law, or to abbreviate it, NK1. You guys remember what the first law of Kepler's planetary motion was, right? What was that first law again? Just a quick test here to see if you're remembering things. Sage?
The Earth goes in a elliptical orbit with the sun on a focus point, not the center.
Great. And we'll just call that the law of ellipses. You guys will remember that Kepler did not know or have a concept in mind called the force of gravity. So for him, especially with his propensity for mystical thinking, the planets were attracted to the sun by some magical living vitality that inhabited the solar system. Who knows what kind of astrological crystal meth he was smoking, okay? Newton could now see that gravitational orbits did not just apply to, say, the planets in the sun, but they applied to moons in orbit around planets, and they could even apply in weird places like asteroids and comets, and maybe even other stars interacting with one another. Consider, for instance, the situation involving a binary star orbit. And in particular, I'm thinking of the closest star to Earth, Alpha Centauri. Alpha Centauri is actually a binary star system in which, amazingly, both of the stars are almost exactly equal to the mass of the sun. It's pretty incredible because stars can have a wide range of masses, but both of these are binaries and both of them have the same mass as the sun. If you try to think about that from Kepler's point of view, you quickly run into a problem. If M1 and M2 are the same, how do you figure out who's on the ellipse and how do you figure out who's at the focus point? Would M1 orbit M2 on an ellipse with M2 at the focus point? Or would M2 orbit M1 on an ellipse with M1 at the focus point? Who's on the ellipse? Who's at the focus? Kepler's first law doesn't have a way to deal with that. Do either of the Ryans remember what the correct solution to the problem is?
Isn't it like, isn't the focus point not on one of the stars, but in the center of both stars, or?
If they were exactly equal, that would be in the center.
Okay,
If they are not equal, that weighting point needs to be shifted, and now we need a new vocabulary term to describe this thing. It's called the center of mass. The center of mass is like a balance point that's weighted by the ratios of the masses. If I showed it to you mathematically, you'd probably get annoyed with me. So instead, I will do this in cartoon form, which is really actually better in some ways. If star 1 were, say, 4 times more massive than star 2, the center of mass would shift to 1/4 the distance between the two stars. If star 1 was 10 times more massive, the center of mass would then shift to 1/10 the distance between the two stars, and so on and so forth. It's a center that's weighted by the ratio of their masses. Consider the situation of the sun and Earth. The sun is literally 1 million times more massive than Earth. 10 to the 30, 10 to the 24 is 10 to the power of 6. That means the center of mass of the Earth-Sun system is shifted to 1/millionth the distance between the center of the sun and the center of Earth. Then again, I happen to know that the radius of the sun is only, the center, I can't do this here. In the case of the sun, the radius of the sun is 700,000 kilometers, but the center of mass of the Earth-Sun system is 1/1,000,000 of 150 million kilometers, and therefore should only be 150 kilometers from the center of the sun. And you can clearly see that 150 kilometers is way the hell less than the radius of the sun. So the center of mass of the Earth-Sun system is actually a point inside the belly of the sun, which means Earth, and this is why we have to modify Kepler's laws. It is not correctly true to say Earth orbits the sun with the sun located at a focus point. Earth orbits a point inside the belly of the sun with the point inside the belly of the sun at a focus point. And also the sun orbits a point inside the belly of the sun with that point at a focus point. Or in other words, a more elegant way to say it is that the sun wobbles on its axis due to gravitational tugs from the other planets. The primary source of the sun's wobble is due to the planet Jupiter, which has the greatest mass in our solar system, okay? The second order effect is actually tied between Saturn and Earth. So let's think about this. Saturn's mass is 100 times that of the Earth, right? But Saturn is 10 AU from the sun. Gravity falls off as 1 over the distance squared. 1 over 10 squared is 100th. So the gravitational force of Saturn and Earth are actually the same on the sun. So Earth and Saturn's gravity kind of compete for the next wobble, and all the other planets add a tertiary wobble. In fact, this would be the wobble a star would experience in a circular orbit with just one planet. In a multi-planet system, the stars actually wobble in a chaotic rosette pattern, which is actually convenient because this is what we use to discover planets outside of our solar system. When I was an undergraduate student sitting in the chair just like you guys, we knew of 0 planets for certain that existed outside of our solar system. Today, we have discovered over 5,000 confirmed planets outside of our solar system, which is kind of cool to just see over my own career, that change. It's very cool in its implications because it suggests that probably every stupid star in this galaxy has a planet around it. And that means the probability of one of those things having some creepy crawlies on them is super, super high, right? So there's some cool implications for this. Those planets are too small to be seen through a telescope, but we can see the stars, and by measuring their wobble, we can infer the masses of the planets which are around them. This is related to Newton's version of Kepler's first law. Now, there's another part to this, at the risk of boring you guys. Newton discovered that not only were circular and elliptical orbits possible, but for the first time ever, Newton was able to calculate that it's possible for gravity to create other types of orbits, which we call unbound orbits, and they also obey conic sections. This is what you might call a gravitational slingshot. Gravity can deflect the path of a particle moving quite fast nearby, and it will bend its trajectory either into a parabola or a hyperbola, depending upon the velocity and the distance between the object and the star. So these are called gravitational slingshots. And because Newton's mathematics was more advanced than Kepler's, he could see that unbound orbits were also a gravitational solution. How then should we best express Newton's version of Kepler's third law? Let's try it something like this. The law of ellipses enhanced would say 2 masses orbit each other on, instead of an ellipse, we would say conic sections. That's the group class. And conic sections include circles, ellipses, parabolas, and hyperbolas. 2 masses, apologies. 2 masses orbit each other on conic sections with the center of mass at a focus point. I think you guys can also see why we still keep Kepler's laws around. This is a very techie and gobbledygook way of saying something that usually boils down to what Kepler said. Usually the two masses are a big fat star and a little tiny planet. Usually the star is essentially the center of mass, and usually the conic section is typically an ellipse. So Kepler's law is a more restrictive version, but this is the more encompassing, correct description, right? All right. What about Kepler's second law? Someone just tell me the title of it. I thought the Ryans would have this memorized, but what the shit do I know?
A planet, oh, the law of equal areas. A planet sweeps out equal units of area and equal units of time.
And one of the shorthand phrases to describe this is equal areas in equal times. When Newton analyzed this problem using the law of gravity in calculus, he discovered something pretty dope, that this law was strictly true and it required absolutely no modification. It was perfectly true. But what was neat is that his analysis showed that there was a reason for it, which Kepler could not see. That reason is a key concept in physics that goes by the name of the conservation of angular momentum. This is a big topic in physics and a big topic in astronomy. So big, in fact, that I'm not even going to touch this today. That requires its own special discussion. I've told you the reason, so you can meditate on that, but we'll come back to that at a later time. We've got a bigger fish to fry today. Our fish to fry is NK3. This is the key formula that we've been building up to study today. In fact, NK3 is probably the whole purpose of today's lecture. It's a key formula in astronomy that lets you do wicked useful stuff. Let me preface this by saying that Kepler kind of cooked the books with his third law, p squared equals a cubed. He basically invented the astronomical unit so that he didn't have to think too hard about the relationship between distance and period. And as an example of why this sort of came back to bite him in the ass, Kepler, Johannes Kepler, was a contemporary of the famous Italian scientist Galileo Galilei, who I mentioned earlier with the inclined planes. Galileo was not only famous for his inclined planes, but was also famous for the fact that he built the first telescope for astronomical purposes. And when he built this telescope, he began making discoveries by peering around at those planets that people had looked at for thousands of years without understanding them. And what blew his mind was that he discovered that when he looked at Jupiter, there were 4 little orbiting satellites that looked like tiny stars. He actually called them the Medicean stars after his patron who gave him the money to build the telescope. Today, of course, that guy got the boot, and now we call them the Galilean moons, which is quite funny, right? These moons, and by the way, this is a picture from Galileo's very own journal. This is the handwriting of Galileo. He's writing this in Italian. And he sees the planet there, and he can see the Medicean stars. And night after night, he's watching as the stars drift back and forth around the planet Jupiter. To Galileo, this was a holy shit moment, because he could finally prove that it was possible for things to orbit something that wasn't Earth. Therefore, he could sort of infer that not everything needed to orbit Earth, and Earth didn't have to be the center of the universe. This was one of his arguments for the Copernican theory of the solar system. He was a contemporary of Kepler, who lived in Germany at the time. They were both famous scientists of their day. So he wrote a letter to Kepler, who was also a known Copernican, and said, bitch, check this out, okay? I found myself, sometimes I get a little too crude in these lectures. Sometimes I found a bunch of moons orbiting this planet, okay? And that means that things don't have to orbit Earth. Don't you think that's cool? And Kepler wrote him back, and Kepler said, dog, you got to try my p squared equals a cubed on that thing and see if it works. So, hey, Galileo, will you measure their periods and measure the distance between the moon and the planet and tell me if the square of one is proportional to the cube of the other? Galileo said, I guess I could do that. He tried it, didn't work. And then Galileo lost respect for Kepler and threw some shade his way. It was like, this guy thinks he knows what's going on in the Copernican solar system. He's got this nutty formula that doesn't even work. And that actually cost him some points. Of course, the problem was that if you change the central or larger mass, it will drastically affect the relationship between these two things. But without the concept of gravity, he couldn't even comprehend why it would matter that Jupiter did not have the same mass as the sun. It really required Newton, who had knowledge of the idea of gravity, to modify the formula correctly. And when he did, Newton discovered that he could make it work for any orbiting systems. And weirdly, that Kepler had kind of been right, but he just needed an extra term or two to account for gravity. This is the more complex yet more correct version of the formula. They call it Newton's version of Kepler's third law. That's TLDR for my tastes. I call it NK3. It has a p squared on one side, an a cubed on the other, but a term that essentially involves big G and the sum of the masses. Let's write that down here. Newton's version of Kepler's third law is p squared equals 4 pi squared a cubed over G times the addition of the two masses. And be careful, that addition means something. It's not the same as the force of gravity. We got to analyze this, and then we're going to use it for our lab today. Let me keep an eye on the time here. Shoot, 3:05. Okay. The lab we're going to do today is basically a glorified sample problem. But I would like to do one last little bit of notes involving units and things. Before we do today's lab, let's have a compare and contrast between Kepler's and Newton's version. This matters to you guys because you're going to have to toggle back and forth using these two different formulas. And unless you have a lot of experience, it's not going to be obvious at first which one to use. So there's Kepler's third law, and then there's Newton's version of Kepler's third law. First, let's just write them down so we can see the difference. In Kepler's third law, you have p squared equals a cubed. In NK3, you have p squared equals 4 pi squared a cubed divided by big G times the sum of the two masses. All right, first let's talk units. Let's test you guys. What are the units of P and A in the Keplerian version? What is P and A?
P is in years and A is in astronomical units.
Thank you, Ryan Dick. Very good. And this is practical, useful stuff. Okay, Ryan, do you remember from last semester what we want for the units of NK3?
I'm assuming P and A are the same as Kepler's third law. They're year and astronomical units.
Ryan, the fact that we have big G in there,
yep.
Remember the units of big G are meters cubed per kilogram per second squared. NK3 is an MKS formula. So why don't you revise that and try again, Ryan?
Yep. Would P be in seconds?
Correct.
A would be in meters.
Correct.
And then the mass would be in kilograms?
Exactly. This is really important for you guys because you're going to have to convert to drastically different units depending on which version you want. Let's talk about where they apply. This works for objects that orbit either A, the sun, or B, an equal mass star. That means it will work for planets. It will work for comets. It will not work for moons. And in general, it will not work for binary stars. And these are the contexts in which you guys will be using them. NK3 is cool because it works for any two masses that are in orbit with each other. However, it's more complicated to execute. So in general, whenever you're confronted with planets or comets, you want to revert to the more simple p²=a³. One more point, then we stop. This is not the most useful form. In fact, you're being introduced to this formula in this fashion because you were introduced to Kepler's law like so, and you're seeing the relationship. Astronomers need this formula for a completely different reason. From an observational astronomy point of view, it is a relatively straightforward thing to measure the periods and somewhat the distance between two objects. Just as Galileo did, you can go to your telescope, you can watch moons orbit back and forth in front of your planet, and you can measure their periods. Take the moon, let it go back and forth, and pow, you measure the period. You can also measure their angular displacement from the planet. That's an angle. And then you can convert that to a distance using the small angle formula. So it's actually possible to directly measure both the period and the distance of orbiting bodies. The mass, however, is virtually impossible to determine through any other means. So the real value to astronomers is that we often use NK3 solved for mass. We'll be doing this in our homeworks come Tuesday, which is why I wanted to squeeze it in. And that version of the formula looks like this. M1 plus M2, the total mass of the system, is 4 pi squared a³ divided by g times p squared. This formula is so essential to astronomy. It's so important for all of the work we do that it is a keystone formula that unfortunately must be impressed upon 101 level students for them to even understand what kind of stuff we do. The little nickname they sometimes give it is they call it Newton's balance beam. Because without realizing it, Newton had discovered a tool that astronomers could use to measure the masses of stars far from Earth or the sun. Okay, obviously we should try a sample problem with this. I've basically turned that into a lab. We're going to calculate the period of the International Space Station. There's only 3 of you. I did think about farming this out to the pre-recorded lecture, and honestly, I've got some work to do today, so I'm very, very tempted to do that. I owe one of my colleagues a report, a peer evaluation, but also I could do it with you guys. What do you think? What are your thoughts about this?
Personally, I'm okay either way, so my opinion is really just up to you.
Same.
Same.
Well, I love that you guys are here with me all the time. And so in a sense, I would really hate to let you down. On the other hand, if it really doesn't matter either way to you, it would kind of help me I want to get this into them before 5 o'clock. So that extra hour would mean I have 2 hours to finish instead of 1. You know what I mean? I'm actually already a day late, so I'm kind of feeling bad about it. So I'm a little bit in emergency mode here. So if it's really all the same to you guys and you won't take it personally, could I give you the pre-recorded lab the same way that I did with Ian? I hadn't planned on doing this until just now, but the stress of this report is sort of hanging over my head. You know what I mean? All right. I think then if that's all right, I'm going to exercise that right today. It'll take the same amount of time for you guys. It kind of won't matter, right? And it'll actually save my butt. So with that in mind, let me get you the precise timestamp. I think we already kind of saw the link because I shared it with Ian earlier, correct? Now listen, you guys got to promise me that if I do this, you won't flake on it, but you'll actually just watch the video and do the math. Can you guys promise me that? The other students have to do this. All right, here we go. So that's the correct time right there. That's 1:44. I want to copy the URL at the current time, which is 1:43:54. Chat you. And I'm going to put this up on Blackboard as well. That link takes you to the correct time. The more I think about it, the more I think this is a really good idea because it's the same more or less for you guys. It's mostly me talking anyways. And I have to do this. Like I'm under some stress right now. All right. So please watch that video and submit lab 4. I hope you guys have a great weekend. Tuesday, we'll get together at 10 a.m. to do this very important homework number 3. Okay? All right. Okay, guys, thanks for understanding. I really appreciate your letting me off the hook here. And anything else before we go?
Best of
I'd
luck.
like to-
Have a good weekend.
I'd like to remind all of you guys, sorry, this week you owe me homework 2, lab 3, and lab 4.
Mhm.
Okay.
Cool.
All right, guys, good luck. Get that done and don't delay so that you can enjoy your weekend, okay?
You too.
Bye, everyone.
See ya.